Oh no, Crow. Oh no. Ah, there you go. You'll be fine, Crow. You'll be fine. What happened? Crow has a midterm. Crow has a midterm at 10:45. Always a unpleasant feeling. Yeah, always an unpleasant feeling. All right. Um, Welcome back, class. Uh, Come on in, have a seat, coffee. Because continue where I left off. As some people like to call it, ranting about normal subgroups. Yes, in this case. So I'm going to continue my ranting, my usual rant. Mathematical rants. Oh, hello, RB3. Good to see you. So let's continue. I have these three objectives for today. Conjugacy classes, whatever that means. Then part 2, we'll prove a fun theorem. We'll see the power of knowledge of normality. Okay, so this will be fun. Fun/cool. This will be basically a definition. And this will also be a definition. Okay, so that's what we have in store for today. Let's start with this definition. What the heck is a conjugacy class? Okay. So what the heck is a conjugacy class? My handwriting is mostly good, folks, please. Okay, definition. Conjugacy class. Alright, so suppose A is an element of a group. Then the conjugacy class of A is the set I'll just call it conj A. That doesn't mean anything yet. It's the set of all conjugates. Okay? Alright, let me show you an example real fast. The new music playlist. I pressed the shuffle button, arbitrary. I discovered that on Spotify, there's a button like this. Simple transposition. There's a simple transposition that you can activate. And I discovered that the other day. Alright. Yeah, SN. SN is generated by shuffles. Keep clicking the shuffles. It'll generate all of SN, arbitrary. Awesome. Good. So let's see here. Next. So let's do an example. For example, the conjugacy class of the identity element is just the identity element. Singleton. Here's an example. Let's do another example. It's not really an example, it's an observation. If the conjugacy class of A is only A itself, notice that A itself is in the conjugacy class of A, because you can take identity times A times identity inverse. That's conjugate. So if a conjugacy class is just a singleton, then A is in the center. Oh, I think we use Z. Center. All we're saying, and we're just saying the same sentence as A commutes with everything. This sentence is the same as G times A equals A times G. These are the same sentences. So whenever you see a conjugacy class that's super tiny, namely a singleton set, you're looking at an element of the center, and it's if and only if. It's a if and only if. Of course. All right. So there's some examples. I computed some conjugacy classes. Actually, in office hours last office hours, which I recommend that my students go to if they are falling behind or feeling like they're not getting the group theory. So in office hours, the conjugacy classes in SN are in bijection with just cycle type. And cycle types are just like basically partitions of the number n. Ways of writing n as a bunch of numbers. Let's say okay, just ways of putting parentheses where you just record how many of each parentheses size you have. That data is exactly the data of conjugacy classes. Okay, so that's office hours, last office hour. Okay, and a good question was asked. Do I know how do I have perfect clarity on what conjugacy classes in AN look like? And I dug it up from old textbook, and now I know. Now I remember. So I'll present that tomorrow, either during class at the end, probably not, but office hours for sure. And it'll be important that we study that fun problem. What is the relationship between the conjugacy class and the centralizer? Okay, no. I don't want to talk about the centralizer. I just want to stop right now with with just the center. The center. I just want to use this observation today, but that's a good general question. Okay. All right. So okay. I want to make one more observation. Fancy words. A conjugacy class is simply an orbit. There's a fancy word, right? Orbit? That's fancy. Or B is an orbit of orbit in G under the conjugation action. Of G on G. Literally, you take this element A, act on it by conjugation, and see the full range of other elements you reach. That's an orbit. This is an orbit under the conjugation action of G on itself. Awesome. What a conjugacy class is. And so this is super general. The group G is a disjoint union of conjugacy classes. Whenever you have a set on which a group acts, the set decomposes into a disjoint union of the orbits. Same with this specific context. So these are just simple observations. Just, of course. Okay, good. That's all I want to say about conjugacy classes. They partition the group G into sets. They're not subgroups. I'm not saying that these things, they're just orbits. They're just subsets. They partition the group. Good. If you have a very small conjugacy class, namely a singleton, you are witnessing an element in the center of the group. All right, that's all I want to observe for now. Let's go back. Conjugacy classes. Okay. Let's do something fun and cool now. Let's do something fun and cool. Let's do something fun. A fun, cool thing. We can prove now. And I just want to highlight the flavor, what it feels like when you have in your possession a normal subgroup. I want to indicate the power of those little tricks that I showed you last class. Okay, so here's a theorem that we're going to prove. If G is a group of order p squared, p is a prime, then G is either isomorphic to the cyclic group of order p squared, or G is isomorphic to this one. In particular, G is abelian. There are no non-abelian groups of order p squared. Okay, let's try to prove something like this. So the first thing I want to show you is an interesting and powerful general fact. So here's a lemma. Here's an important lemma. Suppose G is a group of order p to some power. Then the center of G is non-trivial. In other words, it's not the identity subgroup. It has more than the identity element in it. Okay, so how does this lemma, how do you prove this lemma? This lemma is an orbit stabilizer. This lemma comes from orbit stabilizer mathematics. Okay, so let's do the proof of this lemma. Consider the action of G on itself by conjugation. Okay, the set G is the disjoint union of orbits or conjugacy classes. Okay, so the number of elements in the group is equal to the sum of sizes of conjugacy classes. Each conjugacy class is an orbit. Okay, but by orbit stabilizer, the size of an orbit must divide the size of the group. I know, Crow. I know that. But they have these massive libraries of books behind them, and if you enhance the video, Crow, it's clear they haven't opened like half of them. They're like pristine condition. Have you noticed that? Okay. Anyway, I don't want to call anyone out, but All right, so the conjugacy classes, you add up the sizes, they add up to the total, the size of the group. Each conjugacy class is a number, the size of each conjugacy class divides the size of the order of the group. Okay? So, every conjugacy class either is a singleton or has size divisible by p. Okay? Now, last little observation. There is at least one conjugacy class which is a singleton. Namely, the one for the identity. This set. And so now let's look at this. Oh, you want a twisted cubic? All right, Brainstorm. Thanks for following earlier. Okay, here's your twisted cubic. Okay, but let me just continue lecture. So there's at least one conjugacy class of size 1. The identity forms its own little conjugacy class. And so now if you look at this observation, so in this equation, if you look at the sizes of both sides, the left side is divisible by p. The right side is a bunch of numbers divisible by p plus a bunch of ones. So what we conclude is, since there's at least one 1 on the right hand side, there has to be at least p actually. That means that the center of G is non-trivial. Okay? So, a group whose size is a power of a prime has to have some interesting stuff in the center. That's a great important little lemma that's used a lot. Hey, Arbitree, teacher's pet. I hope you're enjoying your, I don't know if your new job has started, but I hope you are enjoying your life. Congratulations again. I'm very happy for you. Okay, next. Let's build some other pieces of knowledge to get to our theorem. So next, here's another. This is an observation. The center is a normal subgroup, folks. The center of a group is a normal subgroup. This is super general. This is so obvious. Look, if you have an element in the center, and if G is an arbitrary element, then of course conjugation remains again in the center. Because this stupid. Okay, so center is a normal subgroup, folks. All right, let's go back and see what were we aiming for. We have this observation: center is a normal subgroup, and if you have a group whose number of elements is a power of a prime, there's a name for this. It's a P group. P group. Okay, its center is non-trivial. Okay, so we want to prove this theorem. If G is a group of order p squared, P group in particular, then it's either this or that. Okay, so what we're gonna show is, okay, so let's do that. Let's aim for that theorem now. Theorem is close. Okay, usual case check. Ready? Do I take DE lessons, Professor? No. I don't. Oh, do I teach differential equations? Not this semester and not next semester. I know what I'm teaching next semester mostly, so I don't think I'm teaching differential equations. But I have taught it. What level math is this? It's algebra. Okay, so the theorem is close now. Ready? Okay. Pick an element. In this group of order p squared. If its order is p squared, then you're done. It's cyclic. You have a cyclic group. And mod p squared z. Okay. So we're down to the situation. We're in the situation where every element of the group has order p. Every non-trivial element. So we can assume every element, non-trivial element, has order p. Okay. Now, okay, so we can assume every non-trivial element has order p. So what the heck am I doing? Right. Okay. So so consider the center. This group is either a cyclic group of order p or it's the whole group. In which case G is abelian. And then we will deal with that case separately. I mean, secretly, we're going to be in that case no matter what. So we're gonna arrive at this situation at the end, okay? So it's either all of G or it's a cyclic group of order P. Okay? So it's isomorphic to Z mod PZ, this center. Let's consider the latter situation. Let's case. Right? Well, pick any element that's not in the center. G minus, this is minus, not quotient. Complement. Pick any element in the complement and consider K, which is the cyclic subgroup generated by it. It's a cyclic subgroup of size P. That's our assumption. Okay? Okay. K acts on the center by conjugation. Since the center is a normal subgroup, K acts on it by conjugation. i.e., we get a homomorphism. Conjugation homomorphism. From K, which is isomorphic to Z mod PZ, to automorphisms of the center. The center is isomorphic to Z mod PZ. That's our assumption. That's our case. That's our situation that we're pretending. All right? However, in homework problem, last 2 weeks ago, I don't know, last week, I asked you to find the order, the size of the group of automorphisms of a cyclic group. This group has size p minus 1. If p is a prime, the automorphisms of z mod pz form a group of order p minus 1. Namely, you can send the element 1 in z mod pz to any other element that's not 0. And that'll form a homomorphism, an isomorphism, from z mod pz to itself by extending. Okay? So go and try that homework assignment again if you failed. So this group has size p minus 1. And this is a group, this is cyclic of size p. So ask yourself, where can a generator of k go? A is a generator of k. It has to get sent to an element of order dividing p, because it has order p. So wherever it goes under homomorphism has to be an element whose order divides p. But there is no element of order p in a group of size p minus 1. So where can A get sent? Only to the identity map. The identity automorphism. Because of order considerations. There's no room for an order p element in this automorphism group. So conjugation action of k on this group is trivial. So the conjugation action is trivial. In other words, k and the center commute. And are disjoint. We get but this is a contradiction, because the left-hand side is abelian and the right-hand side center was assumed to be smaller. All right? There are many similar types of situations where this kind of act by some subgroup on a normal and deduce that the action is trivial. Actually, I just realized that I'm being stupid in this proof, but I still want to highlight, when you have a normal subgroup and you act on it, you can sometimes just by soft methods tease out that the action of conjugation is trivial on it. In this case, I was being super stupid. I just realized. So you can laugh at me. But go ahead and only just take this part. This tool. Pay attention to the use of this tool. Okay, so this case is actually not possible. In fact, the center has to be the whole group. And so G is abelian. And now we have to pin down that G is Z mod P is isomorphic to Z mod P cross Z mod P. What's left? So for this, same kind of H times K trick number 7 that I showed you yesterday. So here it's like pick A and G. Pick 2 elements, which we are assuming everything has order P or is the identity element. So pick G in here and H in G. H and G not contained in this thing. Then these 2 subgroups don't intersect and 2 obviously commute with each other. And so G cross H is isomorphic to the group G itself by the HK commuting trick. Mod PC cross C mod PC. So every group of, so this finishes the proof. Every group of order P squared is abelian. This will not work for P cubed. This doesn't work for P cubed. This doesn't work for P cubed because you can have the situation where the center is size 2. Oh, sorry, the center is size P. That case does not get removed under the under this when you try to make this work for P cubed. I either got that right or I got the other one. Center can be size P squared. Class, you know that there are non-abelian groups of size 8. So remember, class. There are non-abelian groups of size 8. Like D4, for example. I mean, and the quaternion group, and so on. Well, no, just those 2, right? Yeah, just those 2. Okay? So, something fundamental, there's a fundamental hiccup to trying to extend this to groups of size P cubed. All right, so now, something to ask, some curiosity. Something that you should always have kind of updating in your mind. As we increase the size of G, how much clarity do we have? It's just a game. This is a game that we should play. How much clarity do we have on the set of isomorphism classes of groups? Of that order. Like, there's only one group of order 1, 2, 3. There's just one in each case. 4, there's 2. There's Z mod 4Z and there's Z2 cross Z2. It's a version of this P squared theorem. Okay. 5, cyclic. Every prime we can throw out. Every prime squared we know. Every time we have 2 times the prime, we know the thing. So the first interesting case was actually 8. The first interesting number was 8, but then 9, which I gave for homework and I failed to write it accurately. And then 9 is P squared. 10 is 2 cases, cyclic or dihedral. 11. Okay, 12. 12's an interesting one, really composite. 12 has several possibilities. Maybe I'll carefully analyze it myself first, double check, and then assign it as a homework. But for example, A4 is a new type of group that's not in our usual list of dihedral, this, that, cyclic products of cyclic groups. So 12 is interesting, 13 is boring, 14 is boring. 15, secretly boring. So using normal subgroup type arguments. 16 is interesting. 17 is boring. 18 is 18 is interesting, etc. So you should try to play this game to see how far you can go and get perfect clarity on what group you're witnessing just by the size of the group. It's a fun game. Okay, and it's a fun way to practice the tools that we develop. What levers can you pull when you can guarantee that you're looking at a normal subgroup? All right, so now vocabulary word time. Last thing for today. Vocabulary. So the presence of a normal subgroup in your group is to be thought of as the potential for you to collapse the group to a smaller group. Quotient. To map the group surjectively to a smaller group. So presence of normal subgroup you can think of in your mind as potential for compressing your group to a smaller group, which I'm just going to use the phrase quotienting. All right? And so one natural thing to ask is there a word for a group that has very little potential for quotienting? It's kind of irreducibly small. Is there a word for a group which resists quotienting? Yes. Here we go. Definition. A group is simple if it contains no non-trivial normal subgroups. All right? So you should think of this as incompressible, cannot be collapsed further into a smaller to a smaller group. It's kind of atomic in that sense. It's kind of atomic. All right? So it's just vague feelings we're talking about. And I want to tell you a story now, real fast. Okay, so here's a story. Obviously, Z mod PZ is simple. So that's a whole collection of simple groups. There's no normal subgroup of Z mod PZ that isn't just the identity or the whole group. Z mod 6Z, there are. Because in an abelian group, every non-trivial subgroup, every subgroup is normal in an abelian group. Normality is not an interesting concept in an abelian group. But so if you want simple abelian groups, it's just the Z mod PZ. Okay, so this is simple. But can you find any examples of a simple group besides these? So the first, and this is what we're going to sort of try to understand ourselves. The first example of a simple group is A5. It's a group of order 60. But this is the first example. There's no simple group of smaller size that isn't just a cyclic group of order P. So we're going to try to at least understand that A5 is simple. Why is it the smallest example? That is a huge case check, but it'll use all the tricks that we know to throw at the case checking. But why it's the first example is hard, but why this is an example of a simple group is slightly easier by just getting comfortable writing out the conjugacy classes in A5. So we're going to try to write out the conjugacy classes in A5 and see. There was no possible normal subgroup because a normal subgroup has to be a union of conjugacy classes. We'll see that it's just impossible to form a subgroup by combining conjugacy classes in a union. That is just not going to work out for A5. And that's how we'll witness the simplicity of A5. It's a curious fact that you have to go that far to get to one of these irreducible, non-compressible groups. A5 is the first spot. Okay, the second thing I want to say is that the fact that A5 is simple and A4 is not and A3 is not, that fact is equivalent by 2 semesters that we're gonna slog through. That fact is equivalent to the fact that there is no formula for solving the quintic polynomial, but there is for quartic and cubic. These 2 facts are just like by a wormhole intimately connected. This is a beautiful conspiracy that's being slowly dug up with this first example of a simple group. So the last thing I want to say about simple groups. If you think of simple groups as the atomic groups, the ones that are resistant to quotienting to a smaller group, you think of that, then you might wonder whether there's a periodic table of simple groups. Maybe it's too hard to classify all possible finite groups in this world. But maybe it's possible to give a complete list of the simple groups. And that is one of the huge achievements of the 20th century mathematics. Mathematicians, several, working in teams using computers, controversially, but nowadays probably not controversially, using all the tricks of the trade, really fancy ones that I've never taught you and I've never learned. They just barely were able to give a complete classification, a complete list of all finite simple groups. All right, it's a humongous achievement in mathematics. It's like uncovering the periodic table of elements if you think of simple groups as atomic in this sense. So it's a beautiful story that emerges here, and I'm always happy when I'm at a position where I can explain to students. They know the concepts and the words enough to see like a huge chunk of mathematics rather than some simple little baby theorems that we usually play around with. Okay, so classification of finite simple groups has been achieved with great effort. The biggest of case checks that you could imagine. I know many of you find case checking painful, but that's the granddaddy of all case checks. But it was actually successful, and so we have a complete list of finite simple groups. All right. Okay. So using computers, Kappa. That's right. That was a controversial thing at the time. Some people still think it's controversial, but the case check was fundamentally a discrete thing. And to be honest, I mean, this is not a brave statement. I trust a computer to check more carefully than a peer review journal, a peer who's reviewing a journal article. Way more, like any day. Now, you have to make sure that there are no bugs in the code, but I trust that cleansing process more than the peer review process. Way more. So, they had to use computers for the final case check, but whittling it down was a act of hard mathematics. Okay, so there was a lot of ingenious math to like get it down to merely a case check. But yes, at the end, the computer is needed so far, and no one has a classification method that avoids a computer. So. Okay, Kappa, I will not say that out loud. That's hilarious. I know what you're trying to make me say, but that's hilarious. Okay, that's today's class. Tomorrow, we will look at conjugacy in the alternating groups, conjugacy classes, and I'll try to prove a theorem about conjugacy classes in alternating groups. What do they look like? How do you label all of them? And then we'll try to apply that to A5 and see whether A5 is indeed a simple group, as I claimed. Okay, so that's for tomorrow. Tomorrow will be very, very concrete in the sense that we'll study one particular group. Kappa, you're great. You add so much to this, to the stream, to the community. You can be as degenerate as you'd like. So, be comfortable. Okay. Oh, hello, Toaster. Let me just say hi to people. Oh, hello. Okay, algebraically challenged. Obviously, great moderator here. Smash Time was here. 19 is boring. Yes, 19 is boring. Smash Time. Yes. Oh, he sends a pattern. Is that an Autodesk background? Brainstorm 18. Now, I don't know what that means. What is an Autodesk? Live shoot 1500. Nice try. Okay. Live shoot. I don't think you realize who you're talking to. You are talking to someone who took 3 years of high school Spanish. Okay? ¿Dónde está la biblioteca? That's proof that I took 3 years. 3 whole years of high school Spanish. You have only after the 3rd year can you construct that full sentence. It's the only sentence we learn. So I don't know what you just said there because it's not donde, it's not está, it's not biblioteca. So I don't know what you just wrote. I would need to take the 4th year Spanish to learn what you just wrote. So there you go. Yes, whatever Tropical Geek said, indeed, that. Okay. I'm done for today. Teacher's pet is arbitrary. Wait, this chat can be partitioned into normal, even, and odd degenerate subgroups. Good job, arbitrary. Good use of knowledge. Arbitrary. Good use of this new group theoretic knowledge. Buenos dias, BMP. Good day to you too. What's your math educational background? I am always learning more, Gappy V. I have very little education in math. I am constantly trying to learn more about math. So that's my background. All right. Dictionary in la bibliothèque. See you later today, Tropical Geek. Okay, so I gotta get rid of you. I gotta drop you all somewhere. Where are we gonna go? Where should I drop you? You guys want to make money? You guys want to make money? All right, I'm gonna. You guys should go make some money. All right, go capitalize on this just amazing stock market that's just makes total sense as far as pandemic and everything. Go do that. Go do that. Totally stable. Go. Yes, Mrs. BMP is also calling. Yes, you can hear that? Yes, exactly. All right, so here you go. Go say hi to our good friend Wall Street Booyah. All right? And teach them. ¿Dónde está la biblioteca? Oh man, wait, what? Whatever, we'll do Prof. Peter next time. Okay. All right, cool. So go